This is the periodic table, where atoms are grouped according to their properties. Our ideas about the atom have changed over the years. In this video, we'll look at the first 18 atoms and see how their electrons are arranged. Later, we are going to imagine what it would be like to live as atoms, gaining, losing, or sharing electrons. All the matter in the universe, from the galaxies, stars, and planets, down to buildings and all living things, including our own bodies, are made of extremely small particles called atoms. If we look at a piece of copper closer and closer, we would come to copper atoms. These atoms are made of three principal particles. Extremely tiny electrons move in a cloud around the outside. They have a negative charge. Inside is the nucleus, which is made up of protons and neutrons. The neutrons have no charge, but the protons are positively charged. The charge on a proton exactly balances the electron's negative charge. Most of the atom is space, a complete vacuum. The outermost electrons cause chemical reactions, and this is what we are going to examine. About 3,000 years ago, a Greek philosopher Leucippus and his pupil Democritus put forward the idea of the atom. They knew that by pounding matter, it broke into smaller and smaller pieces. They imagined there was a limit where matter could not be broken up any further. The Greek word atoma means indivisible. Their ideas were not accepted by Aristotle, and this held chemistry back for thousands of years. 2,500 years later, Dalton resurrected the theory by suggesting that atoms are spheres bouncing about with perfect elasticity. He was the first to suggest molecules were made of atoms, and he even drew some molecular structures. Then, Thomson discovered that the atom sometimes ejected a much smaller negatively charged particle called an electron. He got the Nobel Prize for discovering this new particle. To explain this, he imagined that the atoms contained these tiny negative particles inside the elastic ball, like plums in a pudding. His model is called the plum pudding model. Then came a New Zealander, Rutherford. He shot the nuclei of helium atoms at a sheet of gold foil only a few atoms thick. Most nuclei passed right through, but about 1 in 10,000 hit something very heavy and were deflected or even sent right back. To explain why particles pass through, Rutherford pictured the positive charge in a very small core or nucleus, with the negative electrons around the outside held there by electrical attraction. Bohr suggested that the electrons were in orbits like the solar system, but only a certain number could fit in each orbit. Heisenberg found there was no way of knowing exactly where an electron was and pictured an atom surrounded by an electron cloud. Several models of the atom have evolved based on experimental work. Our model represents the arrangement of electrons in shells that surround the atom at different energy levels. Each shell has its own subshells. Atoms are positioned on the periodic table according to the arrangement of their electrons. If atoms lived in a community with their own set of atomic rules, what would life be like? What would affect them? How would they react? Their home, the element settlement, is part of a larger settlement of more than 100 houses. It's a very structured community. There is order to everything and rules to follow. Where we live on the table. Who our neighbors are.
Lovely morning.
G'day, hydrogen. How are you, sodium?
Morning, lithium. Morning, hydrogen.
Where they live is determined by their size and structure, which in turn determines their properties. Similar atoms live near each other. Let's look at the first 10 atoms and the arrangements of their electrons. The smallest atom is hydrogen. It has one proton in the center and one electron moving quickly around it. It has one electron and is placed on the top left of the periodic table. The addition of one neutron forms heavy hydrogen called deuterium, which is quite rare. At times, two deuterium atoms can be forced together, such as in a hydrogen bomb, or on the sun. This forms helium. Helium has two paired electrons in the first shell. This shell is now complete, so helium is placed top right on the periodic table. Adding another proton and electron, the electron would need to go into another shell outside the first. This will occupy a lot of space, so lithium has a low density. This lone electron means lithium is placed on the left of the periodic table. In this video, we're looking at electrons in the atom's outer shell, although in the nucleus, protons and neutrons are always present. If we add another electron, we have the metal beryllium. There are two paired electrons in part of the outer shell known as the s subshell. This places beryllium into the second group of the periodic table. The next element, boron, has 3 electrons in the outer shell. So it's placed in the third group. Carbon has 4 electrons. 2 are paired in the s subshell and 2 are unpaired in the remaining p subshell. And so it's placed in the fourth group. In nitrogen, 2 electrons are paired and there are 3 unpaired in the p subshell. The single p subshell electrons can pair off with electrons from other atoms. In fact, compounds are formed when this happens in a chemical reaction. With 5 electrons, it is in the fifth group. Next, we come to oxygen, which has 6 electrons in the outer shell. There are 2 pairs of electrons and 2 electrons unpaired. Oxygen attracts 2 more electrons in a reaction, and it's placed in the 6th group. Fluorine has 7 outer electrons. It will attract an extra electron to fill this p subshell more strongly than any other element. Fluorine is highly corrosive and is the only element to attack glass. Fluorine is in the 7th group. When the outer electron shell is full, we have neon. All the electrons are paired. If ever an atom were satisfied, it would be neon. It's on the right-hand side of the table. So as you can see, from lithium to neon, an increased positive charge in the nucleus pulls the electrons in closer and closer. Neon is a little bigger. The elements on the right side of the periodic table are all noble gases, commonly known as inert gases. All have full outer shells. Now, back at the element settlement, let's see where they live. The light metals live up on the top left. The heavy metals live further south. And the nonmetals live in this section. The noble houses are on the extreme right. This is part of the noble family: helium, argon, neon. They keep pretty much to themselves.
Help! Someone's stolen my electron!
There are very strict rules, but they don't protect an atom's most prized possession, its outer electrons.
Stop, thief! Come back with that electron!
You'll never catch me, copper!
Nobody's managed to steal any electrons from chlorine. Hers are locked up far too strongly. Still, she's not completely satisfied. Whenever she gets dressed for the Saturday night dance, she puts on 3 layers. First, her underclothes made up of 2 electrons. Then, a bodysuit of 8 electrons. Next is her outer shell of 7 electrons, and here's the problem.
How can I go out like this, with a gaping hole where one more electron could fit? My outer shell's incomplete, and I've no more electrons in my wardrobe. I'll ask my neighbours. They all have beautiful, complete shells.
Oh, I was playing polo the other day, and I lost.
Why, hello, Chlorine. How can we help you?
Well, you all have such lovely complete shells. How can I get one like yours?
You need to dance with another atom, get all close and romantic, then rip off its electron.
Some atoms find that attractive.
Oh, don't waste your time here, Chlorine. You're not strong enough to rip an electron off any of us.
Bet I am.
Okay, come and try it. Come on now, a big, strong kiss. See? Not strong enough.
My small sister Fluorine always gets what she wants.
Indeed, chlorine and her bigger sisters bromine and iodine lock fluorine up before the dance because she's so attractive.
Why am I stuck here all day dissolving the tissues while everyone else is having fun? No one ever sees me, and I'm so attractive.
Argon, how will I find a partner for the dance?
We have already advertised for you. It should attract an atom from the other end of town.
At the other end of town, the next period begins with the elements 11 to 18. Sodium's inner shells are filled with 2 and then 8 electrons. The 11th electron roams freely over a very large space and is held weakly. It could easily be stolen by an atom looking for an extra electron. Sodium is on the left of the periodic table. It has 3 shells, putting it in the 3rd row. Now the pattern repeats itself in the outer shell. After sodium comes magnesium. Its 2 outer electrons are again paired in the S subshell. Next is aluminum with 3 electrons. When we get to silicon, 2 electrons are paired in the S subshell, and 2 are unpaired in the P subshell. Silicon is below carbon, and both atoms have similar properties, with 4 electrons in the outer shell. Everything to the left of carbon and silicon are metals, with 1, 2, or 3 electrons in their outer shell. Phosphorus has 5 electrons, 2 paired and 3 unpaired, and is placed in the 5th group. Sulfur with 6 electrons appears in the 6th group. Chlorine, like fluorine, has only 1 unpaired electron. Chlorine tries to grab an extra electron, but it isn't as attractive as fluorine. This is because chlorine's unpaired electron in the outer shell is further away from the nucleus. All the elements in this group will try to grab an extra electron, but they are less reactive as they get larger. Finally, in argon, the electrons are all paired, and the S and P subshells are full. Argon neither gives nor takes electrons. All subshells are complete in the outer shells of elements in this group. These are noble or inert gases and will not react. Atoms at the other end of town are quite weak and have a reputation for being a bit loose with their electrons. Chlorine could attract any one of them. Loneliness is a terrible thing. Take sodium, for example, an atom with 1 loosely held electron.
Where is everyone tonight? My electron's feeling so lonely way out there. What can I do with a lonely heart? Chlorine atom seeks lively reactive companion with a view to long and stable relationship. Meet me at the disco. What do you reckon, Electron? Go for it, mate!
Xenon and uranium volunteered to be bouncers at the under 18 disco because xenon is noble and uranium is big.
In you go, nitrogen.
Their job is to keep out undesirable elements such as mercury.
Oi, push off, Mercury.
These are carbon. They get in free because they are putting on the floor show tonight. They do amazing acrobatics, forming huge pyramids and some newly discovered acts.
Come on, keep coming up the stairs. Come on, everyone. Last one, come on.
Well, well, ethanol. Why is it always trying to get into under 18 parties? Uranium sent for the coppers.
You called?
Yep. See you, copper.
Ah, here's chlorine.
Has an atom with a good-looking electron been asking for me?
Nah, sorry, Chlorine. We'll send him up if he comes. Evening. Interested in some entertainment?
I should think not.
Chlorine is going to wait for a suitable partner. She can pick and choose at her leisure because she knows she's the most attractive atom at the dance. This is because she has locked her more attractive stepsister Fluorine in her room.
Rotten ugly stepsister.
Now, who should she rip an electron off? Hydrogen is a possibility. They could form hydrogen chloride. Oxygen and nitrogen. Possible, but they are competition. They are both looking around for spare electrons themselves. Oxygen wants 2, and nitrogen 3. Aha! There's magnesium.
Hi, Chlorine. You do feel attractive.
Magnesium has 2 loose electrons. Chlorine could easily take those.
No.
Hi, Chlorine. I can offer you 3 electrons. Say you change your name to aluminum chloride.
I'd prefer to have someone all to myself.
Hello, darling. I'd like to share with 4 of you.
You mean I'd be carbon tetrachloride? No, thank you.
Chlorine could have combined with any one of these, but not on her own. If she waits much longer, she'll have to pair with herself, like the other gases are doing. Hydrogen is sharing its 1 electron with another hydrogen, producing a single bond. The new electron pair hold the atoms near each other to make a hydrogen molecule. This sharing of electrons is a covalent bond. Oxygen is doing the same, but it's sharing 2 pairs of electrons. This is a double bond. Now nitrogen has to share 3 pairs of electrons to fill the hole in its outer shell. It's a triple bond. It's a rule. When gases go dancing, they go in pairs called molecules. Only the noble gases are exempt. Sulfur forms rings of 8 atoms in 1 molecule.
Atoms and molecules. Appearing tonight, the fabulous flying carbonies.
Meanwhile, backstage in the dressing room,
Why do we always have to change our looks just to put on a show? Well, who's accused of this? Well, I wish someone would have put this.
For the first act, the Carboni family will form a flat lattice of graphite. Let's hear it, everyone! Now, in a newly discovered act, they have rolled up the lattice. It's a Bucky tube! And another new act, taking 60 carbons and being the shape of a soccer ball. It's the Bucky ball! Now the grand finale. dimensional lattice, diamond. Hardest substance in the world. Each carbon linked to 4 others. How amazing! Atoms and molecules, we'd like volunteers from the audience. How about the little ones? Have we got 4 hydrogens? That's it, coming close enough to share electrons. Carbon loves hydrogens and will combine with them straight away. Atoms and molecules, may I present methane, CH4.
Carbon has 4 electrons moving around the outer shell. In methane, they form pairs. When 4 hydrogens come and share their electrons, the pairs arrange themselves evenly around the carbon in a tetrahedral shape. Methane is symmetrical.
Now, nitrogen, it's your turn. We have 3 hydrogen. We need a little pressure. Okay, everyone. Squeeze and squeeze. Atoms and molecules. May I present ammonia?
The shape is very similar to methane, with 4 electron pairs arranged evenly around the outside. Even though one pair doesn't have a hydrogen, it still occupies a space. Ammonia has more negative charge on one side, making it polar.
Next, we'd like a volunteer with only 2 unpaired electrons. Thank you, oxygen.
Hydrogen is approaching oxygen, but they find each other repulsive because they are both surrounded by clouds of negative electrons. They need to come closer.
What we need is some heat. And we've got the hottest band in town. That should get some energy into the dance. Bump a little harder, get a little closer. These under 18s move fast when heated. The smaller they are, the faster they go. Okay, once more with energy. And again, faster. And we have contact. And the combination is a boomerang-shaped molecule of water. Yeah!
Once again, there are 4 pairs of electrons, 2 of them with hydrogens attached and 2 without. It doesn't matter which pair the hydrogens are on, the shape is always the same. Once again, the negative charges are more on one side of the molecule than the other, so the molecule is polar.
Now we want to form another non-polar molecule, oxygen and carbon. Could you put your electrons together?
Carbon and oxygen are very similar. They won't combine when they're cold, moving slowly.
More energy, give us more heat. Carbon dioxide.
This time, each oxygen shares 2 pairs of electrons with the carbon, and the molecule comes out straight. Charge is evenly distributed, and the molecule is nonpolar. Normally about this time of the evening, our band has heated the party and the atoms are really jumping. Electrons are loaned and borrowed as atoms look for stable arrangements of their electrons. Meanwhile, Chlorine waits for an answer to her ad. It was getting late. The bouncers wondered whether Sodium would ever turn up. They didn't recognize him when he did.
I've never seen you before.
I live at the other end of town from you.
How many electrons you got?
2, then 8, then 1 in my outer shell.
Sodium? You're big for only 11.
It's this wild lone electron. It goes all over the place. You just can't control it. My hairdresser says it's the worst he's seen.
All right, go on, Indian, but you could lose it tonight.
Go for it.
Inside, Sodium sees the element of his dreams.
Oh, she's nice. I hope that's her. Are you Chlorine? I'm the answer to your ad.
You must be Sodium. Would you like to get romantic?
Okay. But what if we dance first?
Once they were close enough, Chlorine ripped the electron off Sodium and completed her outer shell. Sodium had shrunk to his inner shell, which is also complete. Now, they were both electrically charged and attracted to each other.
I wish I'd been strong enough to insist on a joint account, like other molecules.
Sodium was quite right. Their bond was different to any of the covalent bonds we have seen tonight. It is called an ionic bond. The electron is not shared, but has been completely removed to the chlorine because chlorine is so strongly attractive. Each of the atoms has become an ion and is changed in size and charge and properties. They attract other ions in all directions. They form crystals. The shape of the crystals depends on the ratio of the ion sizes. They grew tired of each other, and by morning they wanted to split. There was only one way out. Water, being polar, lets them drift apart. The atoms now live a new life as separated negative and positive ions. Their outer shells are now complete. Apart from their charge, they have become like the noble gases. There are many stories in this town, and this has just been one of them.
Oi, where do you want these two? 19 and 20.
Oh, over on the left.